Hi, I'm Don from Math Eternal, and I'll walk you through how to defeat the hardest question of HSC Mathematics Extension 2 from 2020. Be careful though, hidden dangers and potential disasters lie ahead. This video will assume that you know these following skills: integration by parts, integration of trigonometric functions, solving factorials with positive integers, and solving trigonometric identities including the double angle formula. Now that we are ready, let's jump in straight into questions. Alright, the very last question of the HSC, 16b. At a first glance, it looks like an integration question with 4 different parts all leading into another in some sort of way or another. Alright, well let's get started with 16b part 1. Let in equals to integral of sine 2 theta to the power of 2n plus 1 with the bounds of 0 to pi over 2, where n is 0, 1, 2, ... Part 1 is prove that in equals to 2n over 2n plus 1, in minus 1, where n is equal or greater than 1. So we want to approach this question using integration by parts. So I'll quickly write down the formula here. So integral of u v dash equals to uv minus integral u dash v. And let's write down what each of these pronumerals are. So u equals to sine 2n 2 theta, and then here if you differentiate it, it'll be 2n sine 2n minus 1 2 theta, and by the chain rule multiply that by 2 cos 2 theta. And now we need to find v, the v dash. So v dash here is sine 2 theta. And now we need to find v, so we integrate this, so that'll be minus half cos 2 theta. Now we just have to solve it. So in equals 2, let's multiply u and v together. So if you do that, I'll put the minus half at the front, minus half sine 2n 2 theta cos 2 theta, and then let's put the brackets around here, pi over 2, 0, and then we need to multiply u dash by v. So we have the constants 2n, 2, and minus half, and a minus in here of course, so that'll convert to a plus, and it'll be 2n integral pi over 2, 0, and then sine 2n minus 1 2 theta, and then since there's cos 2 theta times cos 2 theta, that's a cos squared 2 theta. That's cos squared 2 theta d theta. So that's the equation for in there. And that equals to minus half. Then let's substitute the values. 2n pi cos pi minus sine 2n 0 cos 0. And then I'll just write it here, so plus 2n pi over 2 and 0. And we want to make cos squared 2 theta into sine squared 2 theta. So 1 minus sine squared 2 theta using the identities. So that'll be sine 2n minus 1 2 theta. And then 1 minus sine squared 2 theta. Just like that. And as you notice here, sine pi will become 0, and then sine 0 will also become 0. So that means this whole thing becomes a 0. That'll be 0 plus 2n pi over 2, 0. And then I'm going to split the second bracket, 1 minus sine squared theta, into 2 separate values. So sine 2n minus 1 2 theta minus sine 2n plus 1 2 theta d theta. And then here I'm going to split the integral, pi over 2, 0, sine 2n minus 1 2 theta d theta minus 2n pi over 2, 0, sine 2n plus 1 2 theta and d theta. So now there's one thing that you need to notice, right? So let's go back up to the question. Here, it says that in equals to, so sine 2n plus 1, 2 theta, right? And we find it here. So this is actually equal to in. And then that means that this part would equal to in minus 1. So what we'll do is in equals to 2n in minus 1 minus 2n in. And then by rearranging the equation, 1 plus 2n and then 2n in minus 1. And the final step is in equals to 2n plus 1 in minus 1. And that was part 1 of question B. Now let's move on to part 2. Part 2 of question B is to deduce that in equals to 2 to the power of 2n n factorial squared all over 2n plus 1 factorial. And for this question, what we need to do is grab what we got from part 1 for in and then use the reduction method to get the required answer. And I'll show you what I mean. Let's write down in again. And then here, we are going to find out what in minus 1 is. And to do that, we just have to substitute n with n minus 1 on the top. And on the bottom, same thing. And then in minus 1 is in minus 2. And then we're going to do that one more time. So this is the reduction method. So 2n minus 1. And then here's going to be 2n minus 1, just simplifying the bottom part of the fraction. And then here, 2n minus 2. And at the bottom, I know that's going to be 2n minus 3, in minus 3. And then we're going to skip to the very end. 2n plus 1, 2n minus 1, 2n minus 1, 2n minus 2, 2n minus 3. And then here, dot, dot, dot. We're going to find what I2 is. So I2 is going to be 4 over 5. I1 is 2 over 3. And I0. And we're going to be finding what I0 is later on. And then here, there's a special trick. So we're going to be multiplying this equation by 1 multiple times. And I'll show you what I mean. So here, 2n plus 1. And here, we need to find out what number is lower than 2n plus 1 by 1. So that's just 2n. So 2n minus 1, 2n minus 1. And then here, it's going to be 2n minus 2, 2n minus 2. And we're not actually changing the equation because we're essentially just multiplying the equation by 1. So here, 2n minus 2, 2n minus 3, and then dot, dot, dot. It's going to be 4 over 5, and then 4 over 4, and then 2 over 3, I0. And I just put brackets there because it looks nice and neat, and we know that these numbers are just ones, but ultimately up to you how you present the working out. So here, let's put everything into one big fraction. So big line there. 2n plus 1, 2n minus 1, 2n minus 2, and then 2n minus 3, dot, 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 5, 4, 3. And then on the top, it's going to be 2n. And the thing is, these two numbers are the same, and these two numbers are exactly the same as well. And I assume these two will be as well, and then these two numbers are the same. So what I'm going to do is combine them. It's going to be 2n squared, and then here's going to be 2n minus 1 squared. So 2 bracket n minus 1 bracket is the same as 2n minus 2, just for a heads up. And then here, it's going to be 2n minus 2 squared, dot, dot, dot. 4 is 2 times 2, so I'm just going to write 2 squared, just so we can see a clear pattern here. And then 2 I0. And then here, it's going to get a little bit tricky. So let's start with the bottom. So the bottom is 2n plus 1, 2n, 2n minus 1, blah blah blah, until 3. That's a factorial. With that, it's missing a 2 here. So what we're going to do is, this is going to be 2n plus 1 factorial with 2 factorial on the bottom, because it's missing a 2 and a 1. And on top, let's combine everything into one big square bracket. So 2n minus 1, 2n minus 2, 2, 2, and then whole thing squared. So I forgot to put the dot 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 here. So it's going to be dot dot dot, and then times 2, I0. And then here, 2n plus 1 factorial. And let's move this 2 to the top there, so it's nice and easy to read. So here, it's going to be 2 times 2, so that's going to be 2 squared, and I0 here. And then let's rearrange this bracket, so 2 times dot, so dot 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 2, and then times n minus 1, n minus 2, and then dot 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 2, just like that. And we need to write down that there are n minus 1 terms here, so there's n minus 1 terms, and make sure to write that down. So there's n minus 1 terms of 2, they're all multiplied together, and then here it's just another factorial. So we are very close to the final, the first part of this part of the question, because we still need to find what I0 is. So here it's going to be 2 to the power of n minus 1, and then multiplied by n factorial, and then squared, and then 2 squared I0. I make the fraction line a little bit too long there, and then 2n plus 1 factorial. And then here, looks like I'm running out of space, so I'll write it down here. 2 to the power of 2n minus 2 times n factorial squared. I don't need this part. And then times 2 squared I0, 2n plus 1 factorial. And now we need to find out what I0 is. I can simplify this one more time. It's going to be 2n times n factorial I0 over 2n plus 1 factorial. Now let's find out what I0 is. So let's write down in here. Pi over 2, 0, sine 2n plus 1, and then 2 theta, d theta. And then we need to swap out n with a 0. So here it's going to be pi over 2, 0, sine 2 theta, d theta. And now we just need to integrate this. So this is going to be minus half cos 2 theta, and then bounds of 0 and pi over 2. And then let's substitute the values in. So minus half cos pi plus half cos 0. And we know that cos pi is going to be minus 1, and cos 0 is 1. So here's going to be half plus half, which is just 1. And there you go. Therefore, in equals to 2 to the power of 2n, n factorial squared, all over 2n plus 1 factorial, and times 1, and we don't have to write that down. So now that we are halfway, let's move on to part 3. Here it says let Jn equals to integral x to the power of n, 1 minus x to the power of n, with the bounds of 0 to 1, where n equals to 0, 1, 2, dot dot dot. And part 3 is using the result of part 2 or otherwise. Show that Jn equals to n factorial squared, all over 2n plus 1 factorial. And this question is a little bit tricky because it's hard to first pinpoint how to first approach this question. But we know that from part 1, we solved an integral that looks like this. So we know that x is going to have some sort of sine theta in it. But I know that let x equals to sine squared theta. And as you practice and do more integration questions, you might be able to pick up what x is like that. Alright, so let's get rid of this. Move this to the top here. Dx over d theta, we need to find what that is. So that's 2 sine theta. And then by the chain rule, cos theta. And then dx is going to be 2 sine theta cos theta d theta. And then we need to find the new bounds. So x equals to 1, x equals to 0. And so 1 equals to sine squared theta. And then we know that theta is going to be pi over 2. And then here, 0 equals to sine squared theta. And we know that theta is going to be equal to 0. And these were the same bounds that we got from part 1, which is good news. Let's scroll down. Actually, let's start here. So Jn equals to pi over 2, 0. And then sine 2n theta. 1 minus sine squared theta n. And then here's going to be 2 sine theta cos theta d theta. Let's go down now. Here is going to be pi over 2, 0. And then here, I'm going to simplify this into cos squared theta by using the identities. And then I'm going to move this 2 to the front. That's going to be 2 sine 2n theta cos 2n theta. And then sine theta cos theta d theta, like that. Now let's simplify this. So 2 pi over 2, 0 sine 2n plus 1 theta. Now it looks very similar to what we got in the in part 1. So cos 2n plus 1 theta and then d theta. And now what we're going to do is pi over 2, 0. We're going to add, well, not add, but put this at the front. And then of course we need to divide it again. So 2, and it's going to be 2, 2n plus 1. So we're not actually changing the equation. Then sine 2n plus 1 theta cos 2n plus 1 theta d theta. And now it's going to be 2, 2n pi over 2, 0. And then here it's going to be 2 sine theta cos theta, and then all to the power 2n plus 1 d theta. Let's scroll down. And then here's 1 to 2, 2n. And then here's going to be sine 2 theta. And this is going to be powered by 2n plus 1. And there you go. This part is exactly the same as what we got from part 1. So what we can do is, here we can write 2 to the power 2n, and then here it's going to be, let's see what it was. It was 2 to the power 2n and factorial squared over 2n plus 1 factorial by part I and II. And then here's going to be n factorial squared and then 2n plus 1 factorial. There you go. That was part 3. Time for the final part. Let's move to part 4. So part 4 says that prove that 2 to the power of n factorial whole thing squared is smaller or equal to 2n plus 1 factorial. And the trick to this question is this and this are equal, that and that are equal. So the first step to this question is we let fx equal to x 1 minus x, like that. And we need to find the maximum value of fx, either using the graphing method or the differentiation method. And the graph will be shown here. As you can see, the graph is a parabola where the maximum is a quarter, where x equals to half. Now I'll use the differentiation method. So let's expand that. F dash x is 1 minus 2x. Then 0 is 1 minus 2x. X equals to half. And one more thing. F dash dash x equals to minus 2, which is smaller than 0. So fx is concave down. And now we can say that maximum fx at x equals to half. So maximum fx is f half, which is half 1 minus half, which equals to a quarter. And now we know that, let's scroll down a bit. Now we know that fx has to be always smaller or equal to a quarter. And then we can power everything by n. That's 4 is 2 squared, so 2 squared and then an n there. Let's integrate everything, both sides with the boundaries of 0 to 1. That. Like that. And we know that the left-hand side of the inequality is Jn. And we already solved what Jn was in the last part. So that was n factorial squared 2n plus 1 factorial. And if we integrate this side, that's going to be 1 minus 0, like that. Because if you integrate it, you're just putting an x there. So let's just get rid of all that. And like that. And the very last step is 2n n factorial squared, and then 2n plus 1 factorial, and just last thing, 2n n factorial whole thing squared is smaller or equal to 2n plus 1 factorial. And that was it. That was the last question. Congratulations, you have defeated the hardest question of the HSC from Maths Extension 2 2020. However, I'm afraid that more dangers lie ahead, so it is your responsibility to train hard, level up, and collect experience to prepare for the future. Thanks for the like and sub, and see you in the next stage.